Hey everyone, welcome back to The Explainer. I am absolutely thrilled to have you here today because we're looking at something that powers, well, literally your entire modern life. You know, when most of us think about electrical circuits, we probably picture dry, super complicated math problems written out on a chalkboard. But today, I want you to completely throw that image out the window. Instead, I want you to picture dynamic, glowing, high-speed digital highways. Because honestly, that's exactly what circuits are.
But seriously, think about this for a second. How does energy actually navigate these highways? Whether it's the smartphone sitting right there in your pocket, the laptop you might be using to watch this, or even the battery that starts your car. What is the actual mechanism driving all that invisible energy from point A to point B without causing a massive traffic jam?
To figure that out, here's our digital briefing for today. We're going to cover 1. Pumping charge, 2. Kirchhoff's rules, 3. Series and parallel combinations, 4. Real batteries, and 5. RC circuits.
Okay, let's dive right into Section 1, pumping charge and the EMF source. So, EMF stands for electromotive force, but I'm going to let you in on a little secret straight from the source material. It's actually a completely outdated term. It's not a force at all. Instead, it's way more accurate to think of an EMF device, like a standard battery or a solar cell, as a charge pump. It acts exactly like a water pump, grabbing charge carriers from a region of low electric potential energy and literally pumping them up to a region of higher potential energy.
The source material actually sums this up perfectly, stating, an EMF device does work on charges to maintain a potential difference between its output terminals. And the absolute crucial word in that sentence, work. The battery isn't just sitting there passively. Its internal chemistry is actively doing work on the charges, forcing them to keep flowing and maintaining that electrical pressure difference. It is the beating heart of our entire digital highway.
Moving right along to Section 2, Kirchhoff's loop and junction rules.
To keep all these moving charges from just crashing into each other, we need some strict traffic laws for our neon circuitry. These were established by the 19th century physicist Gustav Robert Kirchhoff, and there's a really sharp contrast between his two main rules. The loop rule is all about the conservation of energy. It tells us that if you go around any complete loop in a circuit, the algebraic sum of the changes in potential has to be exactly zero. The junction rule, on the other hand, is about the conservation of charge. It just means that when a highway splits at an intersection, the total current entering that junction must perfectly equal the total current leaving it. Charge doesn't just magically disappear or pop up out of nowhere.
A fantastic way to visualize this loop rule is to imagine traversing a circuit is exactly like hiking a potential mountain. You start at base camp, right? That's a certain elevation. You gain elevation when you go up through the battery. That's your charge pump doing its work. But then you lose elevation as you hike back down across the resistors in the circuit. No matter which crazy, convoluted path you take around that mountain, when you finally arrive back at your starting base camp, you are at your exact starting elevation. Your net change in elevation is strictly zero. It's just a really beautiful, intuitive way to picture energy conservation in a closed loop.
All right, let's hit Section 3, series and parallel resistor combinations.
Out on this highway, there are two main ways we can structure the components. First up, we have series combinations, where components are just lined up one right after another. Since there's no junction for the road to split, they absolutely must share the exact same current. And the source material gives us a super clever memory trick for this. SIR-I. Series means same I, which is the mathematical symbol for current. On the flip side, we have parallel combinations, where the highway actually splits into multiple lanes. Here, the components share the same potential difference, or voltage. The mnemonic for this one is par-V. Parallel means same V. Seriously, just memorize SIR-I and par-V, and you will literally never get lost reading a circuit diagram again.
Now you might be wondering, why do we even bother memorizing these rules? Well, we use them to find something called equivalent resistance. This is a brilliant theoretical trick where we take this huge, intimidating web of parallel and series resistors and mentally collapse the whole shebang down into just one single theoretical resistor. By applying the SIR-I and par-V rules step by step, we simplify a wildly complex circuit blueprint down to a single loop that we can easily solve with Ohm's law. It takes what looks like an impossible math nightmare and turns it into an elegant, solvable puzzle.
Which brings us to Section 4, real batteries and internal resistance. Because, let's face it, in the real world, nothing is perfect. Real batteries, like the lithium-ion cell keeping your smartphone alive right now, actually resist their own internal movement of charge. So, to solve circuits in reality, we use a quick three-step mental procedure.
First, we identify the real battery. Second, we mentally replace it with a theoretical ideal battery hooked up in series with a tiny internal resistor. And third, we calculate the terminal voltage drop. When a current is flowing, that little internal resistor actually eats up a bit of the voltage before it ever even leaves the battery.
And this resistance explains something you've absolutely experienced firsthand. The rate of energy transfer, or the power, that gets lost to that internal resistor is equal to the current squared times the internal resistance. So where does that power actually go? It gets dissipated as internal thermal energy. This is the exact reason why your phone or your laptop gets super hot when you're running a heavy application or charging it rapidly. The traffic on the digital highway is literally creating friction inside the battery itself.
Of course, if we want to monitor this digital highway without causing a massive pileup, we need the right meters. To measure the flow, the current, we use an ammeter, and we absolutely have to insert it in series with the traffic lane. But to measure the electrical pressure, the potential difference, we use a voltmeter, and we have to connect that in parallel across the component.
And that leads us to our final stop, Section 5, RC circuits and timing the charge.
Up until now, our digital traffic has been pretty much steady state. But in RC circuits, we're dealing with dynamic parking lots, where current and charge actually vary over time. The key concept here is the capacitive time constant, represented by the Greek letter tau. It dictates exactly how rapidly a capacitor, our electrical parking lot, charges or discharges. And here's a crazy fact. If you take resistance, which is measured in ohms, and multiply it by capacitance, measured in farads, the units magically cancel out to leave you with purely seconds. The time constant is literally just R times C.
When you're charging a capacitor, it's not just a boring straight line. You flip the switch, and the capacitor starts at zero charge. But in exactly one time constant, just 1 tau, it rockets up to precisely 63% of its final maximum charge. Then the curve flattens out, slowly approaching 100% as time stretches toward infinity. It's this beautiful, natural, nonlinear exponential growth.
And discharging is basically the exact mirror image. If we take our fully charged capacitor and let all that energy bleed away through a resistor, it decays exponentially. In one time constant, the charge plummets from 100% down to roughly 37% of its initial value. This totally predictable, sweeping curve of time-delayed energy is exactly what allows circuits to have timers, flashing lights, and even memory states. Which leads us to a pretty staggering final thought. We've been talking about smartphones and laptops this whole time, but guess what? The exact same principles, charge pumps, internal resistance, exponential RC timing, and Kirchhoff's loop rules, they govern the electrical impulses traveling through your own neurons right now as you listen to my voice. It really leaves you wondering, at a fundamental, physical level, are we all just incredibly complex, biological multi-loop circuits? It's definitely a fascinating question to ponder. Thank you so much for joining me on this digital highway today, and I can't wait to see you on the next explainer.